Hello student, in this lecture I will discuss about static error constant. When a control system is excited with standard input or constant input signal, then the steady state error may be 0 or constant or infinite. The value of steady state error depends on the type number and input signal. So here, whatever a control system we are exciting with a standard input signal, so that may have steady state error as 0 or constant or infinite, and that steady state error depend upon the type number of the system and the input signal. Okay, so there are three types of static error constant. Okay, so basically the static error constant are figures of merit of control system. The higher the constant, the smaller the steady state error. Okay, so if the higher the static error constant, then the smaller the steady state error. So in a given system, if the output may be the position or velocity or pressure or temperature like this, okay. So therefore, in what follows, we shall call the output maybe it position, or the rate of change of the output maybe it velocity, and so on. Okay, so this means that in a temperature control system, position represents the output temperature and velocity represents the rate of change of the output temperature. Okay, so see, based on this, there are basically three types of static error constant. Okay, so first is static position error constant, second one is static velocity error constant, and third one is static acceleration error constant. So see, static position error constant is always represented by k suffix p. Okay, and this static position error constant or kp is calculated by this equation, where kp is equivalent to limit s tends to 0 gs hs, that means open loop transfer function. Here I have written only gs because I have considered here unity feedback system, that's why here hs equal to 1. So I have only written gs here. Okay, so this is basically limit kp equal to limit s tends to 0 gs into hs. Okay, so see see how we calculate the steady state error of the system for a unit step input. Okay, as we know, the steady state error ESS is equal to limit s tends to 0 SES. Okay, we have already seen this steady state error ESS equal to limit s tends to 0 SES. Okay, and we also knows ES equal to RS divided by 1 plus GSHS. Okay, and here we have considered unit step input. So unit step means RT is equal to UT. Okay, and if we transform this RT, then this is RS, so RS is equal to 1 by S. Okay, so steady state error ESS is equal to limit S tends to 0 S divided by 1 plus GS into 1 by S. Okay, so see here, So see here, this is the equation of steady state error. ESS equal to limit s tends to 0 SES. Okay, and we know ES equal to RS divided by 1 plus GSHS. Okay, so RS is our input, and in this case we have considered input is unit step. So RS equal to 1 by S. Okay, so put this value in this equation. So after putting this value ES in this equation, then we get this equation. Okay, that means this equation. Okay, S divided by 1 plus GS into 1 by S. Clear? So the steady state error of the system for a unit step input is equal to 1 by 1 plus G0. Okay, see here I have considered unity feedback system, so that's why here I have written only G term. Okay, now see the steady state error in terms of the static position error constant Kp is given by ESS equal to 1 by 1 plus Kp. Okay, so this G0 is nothing but Kp. Here I have already seen Kp is equal to limit s tends to 0 GS. Okay, so by putting this G0 Kp, that's why the steady state error of the system for a unit step input in terms of static position error constant is this ESS equal to 1 by 1 plus Kp. Now in this slide I will discuss what is the static position error constant for type 0 system or type 1 or higher order system. So see, in case of type 0 system, type 0 system is there is no pole in the origin. Okay, so type 0 system, for type 0 system Kp is equal to K. Okay, for type 0 system Kp is equal to K, and for type 1 or higher order system Kp is equal to infinite. Okay, so for type 0 system static position error constant Kp equal to K, and type 1 or higher order system the static position error constant is infinite. Okay, so see, for a unit step input the steady state error ESS in terms of static position error constant is 1 by 1 plus K for type 0 system. Okay, and type 1 or higher order system this steady state error is 0. Okay, because for type 0 system Kp value is K, and for type 1 or higher order system this Kp is infinite. That's why for type 0 system steady state error in terms of static position error constant is 1 by 1 plus K, and for type 1 or higher order system the steady state error is 0. Now see how we will explain the static velocity error constant, or what is the formula of static velocity error constant, or how we will find the static velocity error constant. Okay, so static velocity error constant is always represented by Kv, K suffix V. Okay, and this K suffix V is defined by this equation. Okay, so see here Kv is equivalent to limit s tends to 0 SGS. Okay, so see here the steady state error of the system for a unit ramp input. Okay, so the steady state error for unit ramp input is defined by this equation ESS equal to limit s tends to 0 S divided by 1 plus GS and into 1 by s square, because here input is unit RAM, that's why this is 1 by s square. Okay, so this steady state error ESS equal to limit s tends to 0 1 by SGS, and this is basically our static velocity error constant, that means kV. So kV is equal to limit s tends to 0 SGS. Okay, so the steady state error in terms of static velocity error constant kV is given by ESS equal to 1 by kV. Okay, now we will see what is the static velocity error constant for type 0 system, type 1 system or higher order system. So see, for type 0 system the static velocity error constant kV is equivalent to 0, and for type 1 system this kV is equal to k, and for type 2 or higher order system this kV equal to infinite. Okay, so see, for a ramp input the steady state error ESS in terms of static velocity error constant ESS is equal to infinite for type 0 system, and for type 1 system this steady state error equal to 1 by k, and for type 2 and higher order system this steady state error is equal to 0. Okay, now the last is static acceleration error constant. The static acceleration error constant is always represented by k suffix a, and this k suffix a is formulated or calculated by this equation. Okay, so see, the steady state error the steady state error of the system for parabolic input is ESS, and this ESS is equivalent to limit s tends to 0 as divided by 1 plus GS, and here the input is parabolic, that's why here I multiply this term into 1 by s cube. Okay, so after simplifying this we get ESS equal to 1 by limit s tends to 0 s square GS. Okay, and this limit s tends to 0 s square GS is static acceleration error constant Ka, and this Ka is equal to limit s tends to 0 s square GS. Okay, so the steady state error in terms of the static acceleration error constant Ka is given by ESS equal to 1 by Ka. So see, what is the static acceleration error constant for type 0, type 1, type 2, type 3 or higher order system? So see here, for type 0 system static acceleration error constant is 0. For type 1 system it also static acceleration error constant is also 0. For type 2 system this static acceleration error constant is k, and type 3 or higher order system this static acceleration error constant is infinite. So see, for parabolic input the steady state error ESS is equal to infinite for type 0 and type 1 system, and 1 by k for type 2 system, and 0 for type 3 or higher order system. So see, here I have summarized all of my today's lecture in this table, and here I have considered only 3 type of the system: type 0 system, type 1 system, type 2 system. Okay, for type 0 system if we apply step input then steady state error is 1 by 1 plus k, and if we apply ramp input then steady state error infinite, and for acceleration input this also infinite. For type 1 system, the steady state error for applying step input is 0, ramp input is 1 by k, but acceleration input is infinite. And for type 2 system, the steady state error for step input system is 0, and ramp input system it's also 0, but for acceleration input it is 1 by k. Okay, so here I have summarized all of these into one table. So in this lecture I have discussed all the formula to calculate the static error constant. So whenever we are getting steady state error, the static error constant we need to calculate. That static error constant can be depends upon the type number of the system and input signal. So here we are having, or we have seen, there are three types of static error constant. First one is position error constant, second one is velocity error constant, third one is acceleration error constant, and each we will represent Kp, Kv and Ka respectively. Okay, so thank you. Today I stop here.